Hi, I'm Oleksii Oleksenko, and today I will talk about finding speculative vulnerabilities in CPUs. Modern CPUs, they have loads of vulnerabilities like Spectre, Meltdown, MDS, and potentially many others that are yet to be discovered. But how do we find them? Let's say you bought a new CPU. How do you find which vulnerabilities it has? Does it have new previously unknown vulnerabilities? In this talk, we will try to answer this question. And let's begin by analyzing the root cause of the issue, namely the instruction set architecture. ISA is an abstraction that hides the messiness and the complexity of the microarchitecture while maintaining a simple and stable interface to the software. So it greatly simplifies the development of both hardware and software because they can be changed and improved independently. But ISA is also incomplete because by design ISA hides a lot of the CPU behavior. With respect to speculative vulnerabilities, there are two issues specifically. First, ISA hides the macroarchitectural effects. Say we have a load from memory, and the ISA perspective would be that we simply take a value from memory and put it into a register. So the effect of it would be a new register value. Yet in reality, the load is very complicated. It takes a complex path through many parts of the CPU, and in the process it changes their state. So for example, the state of caches or memory predictors or some other parts. So there are two effects actually to this load, the new register value, but also the updated microarchitectural state. And the consequence of it is side channels. If we have two programs running on shared hardware, the actions of one program will change the macroarchitectural state, and the other program will be able to see these changes, let's say through timing, through performance counters, and learn the information about the first program. So this is the first issue, the side channels. The second issue is that ISA hides speculation. For this, consider this program. Here we have a branch that permits memory access only if the address is below 10. So in this example, the address is about 10, it's 100, so the access is not supposed to happen. Accordingly, the ISA perspective would be that there is no load in this program. But in reality, the microarchitecture could implement a branch predictor. We might have a misprediction, the load will be still executed, and it will change the microarchitectural state. So this is the second discrepancy that we have, that ISA tells us the program is executed in one way, but the CPU actually executes it differently. And the consequence of it is speculative vulnerabilities, because this speculation and speculative information leakage is the basic principle that underlies all these vulnerabilities like Spectre, MDS, LVI, and many others. Now to summarize, we have two issues, that ISA hides the macroarchitectural effects and that it hides speculation. But now, how do we fix it? What do we do about it? Here's our solution in a nutshell. It consists of two parts. First, we describe the missing bits in ISA in a form of a speculation contract. And accordingly, our picture will change to this one, where the software now sees not only ISA, but also the contract that describes the missing parts in the description. This way, software becomes aware of these hardware issues and it can react accordingly and implement, for example, software mitigations. But having contract is not enough. Because the contract only expresses our expectations about the CPU, but the actual CPU may or may not meet our expectations. It may still have some hidden vulnerabilities or bugs in the implementation. How do we find those? So this would be the second part of our approach. It's to test the CPU against this contract. And if we find any mismatches between the CPU and the contract, then these mismatches would be violations. These would be potential speculative vulnerabilities that have to be dealt with. So overall, this is our approach, and in our paper, in the paper that I'm presenting, our scope was the second part. So the first part was previously described by previous work. It was presented at Auckland 2021. In this talk, I will mainly focus on the second part. But before we do that, let's actually go deeper into the background and see how these speculation contracts work. So the idea of the contract is to specify these missing bits in ISA, to describe the macroarchitectural effects and speculation. And contracts do so by providing additional specification for each of the instructions that can be executed on the CPU. So to describe the side effects of each of these instructions, we have observation clauses. So observation clause is part of the contract that describes what an attacker can learn from an execution of an instruction. Let's say, for example, we have a CPU with a cache. then this cache is vulnerable to cache side channel attacks, and the attacker from these side channel attacks can learn the addresses of memory accesses. Accordingly, the contract will say that the observation clause will say that loads and stores, so all memory accesses, can reveal their addresses to the attacker through the side channel. So that's the observation clause. Now, the execution clause describes what kind of speculation should we expect on the given CPU. So this is the description of how the CPU can incorrectly execute the program. So for example, if our CPU also has branch prediction, then the execution clause for conditional branches will say that any of them can be mispredicted. Note here that we are not describing the actual mechanism of prediction here. We just say that any conditional branch in a program, it can be mispredicted. That's all the specification that we have. And in total, the contract for this CPU would be that any memory accesses expose their addresses and that branches can be mispredicted. This is the whole contract for the CPU. Now let's go into more details of testing against contracts. This is the actual contribution of this paper. So our goal is to test if the CPU matches our expectations, the contract, and we do so in several steps. We begin by making the contract executable. So that's the first step that we make, is we transform the contract into an executable form. Next, we create random programs and run them on both the CPU and the executable contract. This is conceptually somewhat similar to fuzzing, an idea that is often used to test software. And then, when we have these test cases, we run them on both the CPU and the executable contract and compare their behavior. If we find that the behavior does not match, this is a potential vulnerability, and then we report it to the user. So overall, this concept, the concept of creating random test cases, executing them on the CPU and the contract and comparing them, this is our approach to testing, and we, based on this idea, we built our tool, which we call Revisor, a tool for detecting speculative vulnerabilities in CPUs. And let's look how it actually works in practice and how we build it. To build this approach and this idea, we have to solve several challenges. So the first challenge would be how to record the expected behavior, so the behavior that contract describes. The second one would be to record the actual behavior, so how CPU executes a program. Then how to compare these two. And finally, how to create useful test cases to test the CPU with. And we will begin with recording the expected behavior, creating the executable contract. So to create an executable contract, we take an ISA level emulator. So this would be our approximation of the executable ISA, and we extend it to implement the contract that we are testing against. So we are combining the emulator with the contract and create this executable contract. So in practice, it works like this. Say we have our previous example contract, the one that exposes memory accesses and permits branch prediction. And we run a program on this executable contract while recording the contract observations. So we'll record a trace of observations, which we call a contract trace. And here's what happens. When the contract executes the first instructions, it's just an assignment, so the contract doesn't expose any information to it. Then we hit a conditional branch, and the contract tells us that the branch can be mispredicted, so we take a wrong branch. In this branch, we have a load. The contract tells us that the loads expose their addresses, and so we add the address of this load to the trace. After that, we finish execution, and the result of this execution will be a list of observations that we made. Since we had only one observation in this program, this trace will contain only one value, and so only one value. If we would have more loads, we would have a sequence of values, in this case, the contract trace. Now, that's how we get contract traces. Now let's see how we record the same, but on the actual CPU. Say we have a CPU with a branch prediction, and we execute the same program. This CPU will mispredict the branch and expose its address. So the attacker will be able to learn the address. We call this observation a hardware trace. In reality, though, the attacker doesn't actually learn this address, but the attacker can only observe the changes in the macroarchitectural state. So to emulate that, before starting the execution, in our implementation, we record the macroarchitectural state, Then we execute the test case, this program, and then read the changes. This is effectively a side channel attack. The result of this side channel attack would be not the address of the memory access, but the changes to the microarchitectural state. So for example, this could be a bitmap that represents cache lines in cache. And if one of the cache lines was evicted, the corresponding bit in this bitmap will be set to 1. That's what the attacker actually learned. And so this is how we get hardware traces, so observations on the actual CPU and observations based on the contract. But now how do we compare these two? So how do we compare these traces? The problem here is that a direct comparison is not possible, because a contract is only a loose approximation of the CPU behavior. It's basically a worst case specification, and we can compare them directly. So what we do instead is we compare the amount of information contained in the traces. So if we see that the CPU exposes more information than the contract permits, it's a violation of the contract. And the intuition behind this comparison is as follows. So let's say we execute a program twice with 2 different inputs. If both of the inputs produce the same trace, then the attacker cannot distinguish these 2 inputs, and the attacker cannot learn any information. But if the traces are different, the attacker can distinguish one input from another and can learn some information. So if we see the situation when the attacker can distinguish the executions on the hardware, so produce 2 different hardware traces, but cannot distinguish them on the contract, that's a violation of the contract. That's additional leakage that we did not expect, and we report it. So let's consider an example. Say we have a CPU with a secure branch prediction in this case. So it's not just branch prediction, it's the kind of branch prediction that is not supposed to expose any information to the attacker. So our expectation would be that in the contract that no branches are mispredicted. But let's say the actual implementation of this secure prediction is buggy and it doesn't actually work as we expect it to do. This would be something that we want to detect. We can detect it with the following program. It's a similar one to the previous examples, but this program has one additional memory access before the branch. This program, and we will create 2 inputs to this program. With divergent values of this second address, the one that goes after the branch, which is not supposed to be executed. When we execute them on the contract, we expect no mispredictions, so both inputs will produce the same contract trace, and accordingly there is no information leakage here. But when we execute them on the buggy CPU, it may mispredict, and we will see 2 different hardware traces because of this diverging speculative memory access. This would constitute a information leakage. So we do not see any information leakage on the contract level, but we see information leakage on the hardware level. And this constitutes a violation, and we report it to the user. So this is basically the principle how we find violations in our approach. Now, the final step would be to create test cases. Where do we get them from? So for this, we generate basically random programs and random inputs to them under certain constraints. We make sure that the programs and inputs to them are diverse, so that we are testing different parts of the CPU. But programs, we confine the program so that we don't accidentally jump outside the test case and corrupt the measurements. On top of that, we also make sure that programs are controlled so that we can control the instructions that we are testing, the frequency of different instructions, and so on and so forth, so that we can have controlled experiments. I will not go further into details though. For more details, if you are interested in them, see our paper. It describes them in more detail. So now let's see how this whole approach actually works and it works as follows. So the first step would be to generate random test cases, random programs, and execute them. First, we execute them on the CPU and collect the hardware observations, the changes that they make to the hardware state. Then we execute the program on the contract and collect our contract traces. Then we compare these two. And if we observe an unexpected leakage, so if we observe a mismatch, we report it as a vulnerability to the user. So overall, that's how we build Revisor. Now, finally, let's see how well Revisor behaves in practice. So in our evaluation, we tested 2 Intel CPUs, Skylake and Coffee Lake. And we tested them against several combinations of contracts and in different experimental setups. We began with testing a tiny set of x86, only arithmetic instructions, against a contract that does not permit any speculation. As we expected, we did not find any violations. Then we permitted Revisor to add also memory accesses to the test cases. In this case, in this experiment, within less than 2 hours, Revisor found a violation, and when we expected it, we discovered that it's an instance of Spectre v4. So Revisor managed to find it. Here's an example how it looks. You don't actually have to understand how it works. It's just an example to show you that even with a random instruction sequence, we can find an. Next, we extended the contract to permit the speculation. And we found another vulnerability. This time, it took Revisor much longer to find the violation. In fact, we detected only once in the experiment. It was a new variant of v4. After that, we added conditional branches to test cases, and Revisor found a violation very quickly, within minutes, as we found out it was Spectre v2. So that was our first experiment. In another experiment, we tested a hardware defense against MDS in Coffee Lake. First, we tested Skylake, and as expected, Revisor found MDS quite quickly, within several minutes. But when we tested the Coffee Lake in the same setup, the hardware mitigations should have prevented MDS. Yet Revisor found a violation, which appeared to be LVI, so defense proved to be incomplete. And overall, Revisor achieved what we set ourselves to do. It automatically detected speculative vulnerabilities in real-world black box CPUs. It found the known vulnerabilities as well as a few new ones. In summary, Revisor is a tool that permits us to find speculative vulnerabilities automatically and at scale. Even more importantly, it allows us to establish precise expectations about the microarchitectural security of CPUs, which is the foundation for building secure systems. We hope that with the open source release of our tool, we can positively impact the overall security in shared computing environments. And with this, I want to thank you for your attention, and if you have any questions, feel free to ask us over email or during the live conference.